Hello, geometry enthusiasts. Hey, it is a great opportunity. I'm excited about being here to explore some geometry concepts. I am Justin Patterson, and I am a geometry teacher at Baker High School. And this week and next week, we are going to focus in on some concepts as they relate to circles, and some concepts that have real-world application to them and can be applied to real-world settings. Now, one thing that I love about math and science is that they allow us to make sense of the real world, especially in design situations and design scenarios. Today, the context that we're going to look at circles is going to be in the design scenario of bicycles. Now, how does a bicycle move? That will kind of set the stage for what we need to do, or set the stage for this concept that we're going to look at today. Now, think about this for a second. I have this visual up here of this crank, okay, a bicycle, as there is force that is applied to a bicycle pedal that then pushes the crank, and this crank then turns this wheel. Now, this wheel is called a sprocket. Now, a sprocket is another name for a gear. Now, in this gear, there are these teeth that are equally spaced, and as the crank turns, it turns this gear, which then moves the chain. Now, this smaller gear, it is then attached to the back bicycle tire, which then rotates the tire. So, if you look at the setting that we have here, what we have is two circles. And we have a chain that is moving along the circumference of the circle. So the main concept, the primary concept that we're going to look at today is going to be the concept of arc length. Now, to determine arc length, we need to know some things about what a central angle is and what the circumference of the circle is. So we're going to go ahead at this time and we're going to look at what our essential question is. This is going to give us some direction today for the concept that we'll be looking at. The two essential questions are this: how can I determine the arc length given the central angle measure? And how can I determine the central angle measure given the arc length? And our key terms, key vocabulary that we're going to look at today are central angle, intercepted arc, radius, circumference, and arc length. Now, this problem is going to be set up in two parts. So I want us to go ahead, I'm going to read the problem one time, and then we'll go back through the problem and we'll look at key information. Okay? By pedaling, you turn a large gear through an angle of 135 degrees. Using the diagram below, how far does the chain move around the circumference of the gear to the nearest tenth? Now, I'm going to pause just for a second, and I want us to look at something so that we can visualize this a little bit better. So in the problem, by pedaling, we are turning the large gear first. So the large gear is being turned, and then from there, the chain moves this smaller gear. So the visual here, if we see this, now the illustration that we're looking at in the problem has two gears. If we look at this bicycle here, it has multiple. Okay, we have one gear here plus multiple gears here and here. But for illustrative purposes, I want you to see, here's the pedal in which the force is being applied to, and here is the crank, and it is rotating this sprocket, which again rotates this gear, which causes movement, okay, on the wheel. And just to get a visual for how a bicycle moves. Okay, now back to the problem here. So to have that visual, so here we go. In this diagram, from this crank, it is moving 135 degrees. So its movement is 135 degrees, and this circle has a radius of 6 inches, And this circle, which is the smaller sprocket, it has a radius of 3 inches. So here's what we're trying to do. We are trying to figure out how far the chain moves around the circle. So from this point to this point, how far does the chain move? Now, an important problem-solving strategy. Okay, when we look at something like this, and it is a word problem, a lot of times with word problems, it's easy to get lost. They look very complex for us. It's easy to get lost in all the words of the problem. Now, one strategy that I have found that to be very helpful is the strategy of Pudwick. P-U-D-W-Y-K. I'm running out of space. But here's what Pudwick stands for. Put down what you know. So, put down what you know. We're going to establish what we know first, and that will allow us to then get to what we want to know. So, there's two main things that I want us to pull from this problem that we know. The first thing is that we are turning the large gear through an angle of 135 degrees. Let's hang on to that. That's going to be the first thing that we're going to look at in just a moment. And the second thing is that the chain is moved around the circumference of the circle. That is the second thing that we're going to look at, that it moves around the circumference. Okay, now, let's start with this sprocket being moved 135 degrees. Now, it is moved, the central angle here is 135. Now, I want to stop and talk about this concept of central angle. A central angle is an angle whose vertex is the center of the circle. Okay? That key word central indicates center for us. So it is an angle whose vertex is on the center of the circle. Now, this central angle has a measure of 135 degrees. Now, it is important to note that a central angle is always equal to its intercepted arc. So this arc here is called the intercepted arc of this central angle. Now, a central angle, one full revolution all the way around is 360 degrees. Arcs also have degree measure. One full revolution around is also 360 degrees. So, if this is 135 degrees, this is also 135 degrees. So one important thing to note, that the central angle measure is always equal to the measure of the intercepted arc. Okay, the central angle measure is always equal to the measure of the intercepted arc. Now, down here, I wanted to provide an example and a non-example of a central angle. Now, central angle here, we have angle AQB, and its measure is 60 degrees. And we see also that its intercepted arc AB also has a measure of 60 degrees. Now, I also provided a non-example, because as you work through this unit on circles, you're going to also deal with and encounter these type of angles. And this is different from a central angle because of where the vertex is. The vertex here is on the circle. Now, one thing about an inscribed angle that we will find is that an inscribed angle, its measure is actually half of the intercepted arc. So here, I'll move this out of the way for now. Okay, and we see that this angle is 27 degrees and its arc is 54 degrees. Now that's another lesson for another day, but I wanted you to see the difference between a central angle and an inscribed angle. Now the second thing that we're going to talk about is circumference. Now, what is the circumference of a circle? What is the concept of circumference? The concept of circumference is the distance around a circle. And the formula that we use to calculate the circumference is 2 times pi times radius, or pi times diameter. Now, remember what a radius is. A radius is a segment that extends from the center of the circle to the outside edge. And a diameter is a chord that extends from one side of the circle to the other that contains the center. So, we're going to be dealing with a radius in this problem, but in some of the problems that you will have in this unit, it may be given the diameter. So either form of this equation is appropriate. Now, so let's go ahead and talk about this. What is the circumference of the larger gear? So remember, the larger gear is turned first. What is the circumference of the larger gear? So circumference is 2 pi r. So we have c equals 2 times pi times the radius of 6. So the circumference is 12 pi inches. Now, 12 pi, if you punch that into your calculator, 12 pi in inches, rounded to the nearest tenth, is approximately 37.7 inches. Now, I want us to hang on to that for a second, because in this problem, we're not talking about the full circumference of the circle, but only a portion of it. Okay, so what is the length? And I added 2 letters here to help us label this arc. But what is the length of arc AB? Now, this is the arc AB. And if we recall, the central angle of 135 is equal to the measure of the intercepted arc. Now, I'm going to give the intercepted arc a variable here, and that variable is m. Now, I want you to think about this. Again, this is not the full circumference, but only a portion of it. So, what is the portion of that circumference? Now, in this case, it's going to be 135, but generally speaking, whatever that intercepted arc is our m degrees over 1 full revolution, which is 360. That's going to give us our fraction of the circumference times the circumference of 2 pi r. So let's find the length of AB here. So AB is 135 over 360 times our circumference 2 pi r. Now, if you remember, our circumference that we already calculated was 12 pi. So we have 135 over 360 times 12 pi. Now, if you go ahead on your scientific or graphing calculator, if you punch that, 135 divided by 360 times 12 pi, okay, it should produce approximately, rounded to the nearest tenth, 14.1 inches. So arc AB has a length of 14.1 inches. Now, think about this for a second. This is the answer to our first part of the problem, that when this bicycle sprocket, when it is rotated 135 degrees, that chain moves approximately 14.1 inches. So the chain movement moves 14.1 inches when this main gear, this sprocket, moves 135 degrees. Now, that is going to transition us to the second part of the problem. Now, I want you to hang on to that 14.1 number for arc AB, because we're going to use that again. Okay, so part 2, as the chain moves, it turns the small gear. By using the distance calculated in part 1, remember that's approximately 14.1 inches. We'll use that in just a moment. At what angle does the small gear turn to the nearest degree? Now, again, we're going to Pudwick this. Okay, we're going to put down what we know. And by the end of all these lessons, by the end of this quarter, okay, we are going to be master Pudwickers. Okay, because we are going to Pudwick almost every lesson that we have. We're going to put down what we know. Now, here's what we know here. At what angle does the small gear turn? We are looking for angle measure, and that is important. And we're also looking at the distance around this circle. Now remember, we're now talking about the smaller gear that has a radius of 3 inches. Pay attention to that. So, if you recall, okay, we've already calculated this from the previous problem. The arc length of AB was approximately, let me change the symbol to approximately, 14.1 inches. And our goal here is to find this length of chain that passes around the small gear. Now, that length, remember, to find arc length, find arc length, that is m degrees over 360 times our circumference formula of 2 pi r. Now, let's think about this. What do we know and what do we want to know? Now, in this problem, we are looking for the degree measure. Okay, so we are looking for m. Do we have arc length? Well, we do from the previous problem. The chain has already moved approximately 14.1 inches. So that chain has still moved 14.1 inches on the smaller gear. So this arc length we already know as 14.1. And so we have 14.1 equals m over 360 times 2 times pi times a radius of 3, because we're dealing with the smaller gear and not the larger gear. Okay, so 14.1 equals m over 360 times 6 pi. Okay, now remember our goal is to solve for m. Okay, our goal is to solve for m. So now, the first thing we're going to do is we're going to divide both sides by 6 pi. 6 pi's divide out, and we have 14.1 over 6 pi. So now we're left with this equation. We're left with m over 360 equals 14.1 over 6 pi. So now we're going to multiply both sides by 360. These divide out and become a 1. And so now we multiply this side by 360. Now, we're going to let our calculators do the rest. Okay, so we are going to multiply 360 times 14 divided by 6 pi. Now, when you enter this in your calculator, make sure that you group this together as a full quantity, 6 pi in parentheses. So you should type 360 times parentheses 14.1 divided by parentheses 6 pi, close the parentheses one more time, okay? And you should get approximately 269 degrees. Okay? Now, so let's talk about what that means. That means that when the crank is turned 135 degrees, that it rotates this back gear 269 degrees. Now, how far that it rotates is always dictated on the radius, on the size of the circle. Okay, that is the problem task today. I want to just recap a couple things, okay, before we close. This week, we dealt with arc length. If we want to find the length of an arc, we take the degree of the arc divided by 360, or the degree of the central angle, and we remember that those are the same, times the circumference formula of 2 pi r. Now, next week, we're going to transition a little bit, but we're going to see some similarities between the two. We're going to see some similarities between this formula and the next. Now, next week, we are going to look at the area of a sector. So not dealing with the circumference anymore, but with the area, which is going to be a portion of the circle. So that is coming next week. Hey, I enjoyed this time together today. Looking forward to the weeks to come. Have a great day and stay tuned for the next lesson.